We often assume that witnessing the core mechanics of physics requires multi-million-dollar laboratories or massive particle accelerators. But the wave nature of light isn't something that only happens in a specialized facility. You can prove it yourself with a few items found in a bathroom cabinet. The first thing you'll need is a clear glass electric bulb with a straight internal filament. The second item is a pair of standard metal razor blades. By combining these two everyday objects, you can use your own eye to observe the physical evidence of light traveling as a wave. To start, take the two razor blades and pinch them together between your thumb and forefingers. You are trying to create a microscopic gap between the two sharp edges. The edges of the blades must stay strictly parallel. If the gap is uneven, the experiment won't work. Now hold that parallel slit right up to your eye and look at the bulb. You want to align the gap in the blades so it's parallel to the straight blowing filament of the light bulb. You might need to make micro adjustments to how hard you are squeezing the blades. Changing the width of that gap is what brings the physics into focus. In this setup, the bulb is your light source, and the razor blades are your manipulators. Your own retina is the projection screen where the final pattern will appear. As you look through the slit, that thin line of light from the filament suddenly stretches horizontally into a broad, smeared pattern. At the center of your vision, you'll see a thick, intensely bright region of light. Spreading out from that center, you'll see alternating bands of dark and bright light. You might notice some colors at the edges of these bands. This is because the spacing of the pattern changes depending on the wavelength of the light passing through. If you used a filter to look only at red or blue light, the fringes look sharper. You would also see that red light creates wider fringes than blue light. This visual effect is called diffraction. It occurs when waves bend around an obstacle, like the edge of a razor, and enter the region we would expect to be in shadow. To understand why this happens, we have to look at what occurs when the light hits the razor blades. Instead of traveling in a straight line, the light wave hits the gap and begins rippling outward in semicircles. According to Huygens' principle, we can treat every microscopic point across that open slit as its own new secondary source of light waves. Because these secondary waves start at different points within the gap, they travel different distances to reach the same spot on your retina. This difference in distance is called a path difference, determined by the angle at which light projects toward your eye. The macroscopic stripes you see are simply a visual map of these microscopic waves colliding after they've traveled those different distances. This creates a confusing physical paradox. You are looking directly at a bright light source through an open hole, so how is it possible to see stripes of absolute darkness when the light has a clear path to your eye? This is destructive interference. When the peak of one light wave aligns perfectly with the trough of another, they cancel each other out, leaving behind no light at all. If these waves are canceling each other out to zero, it raises a question. Is that light energy actually being destroyed? Since energy cannot be destroyed, the light missing from those dark bands must be accounted for somewhere else in the pattern. The answer is that no energy is lost during diffraction. Instead, the light energy is redistributed. The waves don't disappear, they are simply moved. The energy that would have landed in the dark bands is added to the neighboring bright fringes. This makes those fringes significantly brighter than the light would be on its own. This redistribution of energy is happening continuously, at the speed of light, right on the surface of your eye. By using two razor blades and a bit of curiosity, you've used the light hitting your own eye to verify the conservation of energy.